There's something moving through our solar system right now that shouldn't exist. Not because it defies physics or challenges our understanding of reality, but because the odds of us witnessing it at this exact moment in human history are so astronomically small that even hardened statisticians pause when they run the numbers. Welcome to Sleepy Earth. Tonight, we're following the path of an ancient traveler that has been sailing through the void between stars for perhaps millions of years. A messenger from another sun, carrying within its frozen heart the chemistry of an alien stellar system. This is 3I ATLAS, and its story is about to intersect with Mars in a way that has astronomers around the world checking and rechecking their calculations. As you settle in for the night, I want you to consider this. In July 2024, NASA's Perseverance rover discovered something extraordinary in the ancient mudstones of Jezero crater on Mars. Patterns in the rock that might, just might, be the signatures of ancient Martian life. And now, as if the universe is responding to our discovery, an interstellar comet loaded with precisely the atmospheric gases Mars lost billions of years ago is approaching the red planet. The timing is so precise, the chemistry so specific that it reads like a cosmic screenplay. But this isn't fiction. This is happening right now, above our heads, in the darkness between worlds. Let's begin our journey into one of the most compelling astronomical coincidences of our time. On July 1st, 2025, the Asteroid Terrestrial Impact Last Alert System, ATLAS, was performing its nightly vigil, scanning the heavens from its stations in Hawaii, Chile, and South Africa. These robotic sentinels weren't looking for visitors from other star systems. They were built to protect Earth, to spot potentially hazardous asteroids before they could threaten our world. But sometimes, when you're watching the sky carefully enough, you find things you never expected to see. The object appeared first as a faint smudge of light, moving against the background stars in a way that immediately flagged it as unusual. Initial observations suggested just another comet, perhaps one from the outer reaches of our own solar system, making its long journey toward the Sun. But as astronomers began calculating its trajectory, something remarkable emerged from the mathematics. This object wasn't bound to our Sun. It was falling through our solar system on what astronomers call a hyperbolic trajectory, a one-way ticket from the stars. The calculations were checked, rechecked, and verified by independent teams around the world. There was no doubt. We had found only the third confirmed interstellar object in human history. To understand what makes something interstellar, we need to think about orbital mechanics. Every object in our solar system, from the smallest asteroid to the largest planet, follows an elliptical path around the Sun. These paths might be highly elongated, taking objects far into the outer darkness, but they always return. They're gravitationally bound to our star, like children on very long tethers. But when an object's orbital eccentricity exceeds 1.0, everything changes. This mathematical boundary represents escape velocity, the point at which an object is moving too fast for the Sun's gravity to ever pull it back. 3I Atlas has an eccentricity well above this threshold. It's moving at approximately 30 kilometers per second relative to our Sun, fast enough that after this single passage through our neighborhood, it will return to the interstellar void, never to visit again. The designation tells its own story. The 3 marks this as the third confirmed interstellar object, following 1I Oumuamua in 2017 and 2I Borisov in 2019. The I stands for interstellar, distinguishing it from the millions of objects native to our solar system. And Atlas honors the telescope network that first spotted this cosmic wanderer. But here's where 3I Atlas begins to differentiate itself from its predecessors. Unlike Oumuamua, which remained enigmatically silent and showed no signs of outgassing despite passing close to the Sun, 3I Atlas immediately revealed itself to be an active comet. Observations showed a clear coma, that fuzzy envelope of gas and dust that forms when frozen materials sublimate in solar warmth. This wasn't just a rock from another star, it was a time capsule of frozen chemistry, preserved in the deep freeze of interstellar space for eons. The discovery triggered a worldwide observation campaign. Every major telescope that could see the object turned its gaze toward this visitor. The James Webb Telescope, humanity's most powerful eye on the cosmos, began analyzing its spectrum. Ground-based observatories tracked its movement night after night. Radio telescopes listened for any signals, though none expected to hear anything from what was clearly a natural object. What they found in those early observations would set the stage for one of the most intriguing astronomical stories of our time. When we look at a comet through a spectroscope, we're essentially reading its chemical fingerprint. As sunlight warms the frozen nucleus, different compounds sublimate at different rates and temperatures, creating a complex mixture of gases in the coma. Each molecule absorbs and emits light at specific wavelengths, creating a pattern as unique as a barcode that tells us exactly what the comet is made of. The first spectroscopic observations of 3I by Atlas revealed something unprecedented. While most comets in our solar system are dominated by water ice, earning them the nickname dirty snowballs, this interstellar visitor was breathing out primarily carbon dioxide. The ratio was striking, approximately 8 parts CO2 to 1 part H2O, among the most extreme ever observed in any comet.
Let me put this in perspective. Imagine you're expecting to find a frozen lake and instead discover a massive block of dry ice. That's essentially what astronomers were seeing. This comet's chemistry was fundamentally different from what we typically observe in our solar system. The James Webb Space Telescope's infrared instruments provided the most detailed analysis. Beyond the dominant CO2 signature, they detected carbon monoxide, CO, carbonyl sulfide, OCS, and traces of water ice that seem to be buried beneath a carbon-rich crust. Each of these compounds tells us something about where and how this comet formed.
In our solar system, different compounds freeze out of the protoplanetary disk at different distances from the Sun, creating what astronomers call ice lines. Water freezes relatively close to the star, carbon dioxide farther out, and carbon monoxide even more distant. A comet's chemical composition can therefore tell us roughly where in its stellar system it formed. The extreme CO2 enrichment of 3I Oumuamua suggests it originated in a very different environment from our solar system's comets. Dr. Karen Meach from the University of Hawaii, one of the world's leading experts on interstellar objects, noted that this composition could indicate formation near the CO2 ice line of its parent star, or perhaps processing by cosmic radiation during millions of years in interstellar space. The surface chemistry we observe might be very different from the pristine interior, like a weathered sculpture whose surface no longer resembles the original stone.
In September 2025, ground-based observers reported something intriguing, a distinct greenish tint to the comet's coma. This emerald glow typically indicates the presence of dicarbon C2 molecules or cyanide compounds. While neither substance is particularly exotic in cometary chemistry, their prominence in an interstellar visitor raised new questions. Were we seeing the products of chemistry common throughout the galaxy, or unique to this object's parent system? The spectroscopic data continued to evolve as 3I Atlas approached the Sun. Like an ancient document being slowly revealed by careful restoration, each observation added new details to our understanding of this messenger from another star. But it wasn't just what the comet contained that captured astronomers' attention. It was where it was heading and when.
Orbital mechanics is often called the clockwork of the cosmos, and for good reason. Once we know an object's position and velocity, we can predict with extraordinary precision where it will be days, months, or even years in the future. The calculations for 3I Atlas painted a fascinating picture. The comet's hyperbolic trajectory was bringing it deep into the inner solar system. It would reach perihelion, its closest approach to the Sun, on October 29th or 30th, 2025, at a distance of approximately 1.4 astronomical units. This would place it just inside Mars's orbit, in the sweet spot where solar heating would maximize the comet's activity. But before reaching perihelion, 3I/Atlas would have a notable encounter. On October 3rd, 2025, the comet would pass within approximately 28 to 30 million kilometers of Mars. To put this in perspective, that's about 75 times the distance between Earth and the Moon. Vast by human standards, but remarkably close in astronomical terms. What made this encounter particularly interesting wasn't just the distance, but the timing. Mars and 3I/Atlas would be on the opposite side of the Sun from Earth during this close approach. This celestial alignment, known as solar conjunction, would render the comet invisible to Earth-based telescopes for several crucial weeks. Just as the interstellar visitor made its closest approach to Mars, we would be blind to what was happening. The European Space Agency quickly recognized an opportunity. Mars Express, which has been orbiting the red planet since 2003, and the Trace Gas Orbiter, operational since 2016, would have front-row seats to this cosmic encounter. These spacecraft, designed to study Mars itself, could potentially observe an interstellar comet at close range, an unprecedented opportunity in planetary astronomy. The geometry of the encounter was remarkable for another reason. As 3I Atlas approached Mars, it would be heating up, its outgassing approaching maximum intensity. The comet would be at its most active just as it passed the red planet, like a cosmic chemistry set bubbling at full intensity within Mars's orbital neighborhood. Calculations showed that while 30 million kilometers might seem like a vast distance, the comet's coma, the envelope of gas surrounding its nucleus, could extend for hundreds of thousands of kilometers. The most diffuse outer portions of this gas cloud might actually brush against Mars's upper atmosphere, though at densities so low as to be essentially undetectable. Still, the coincidence was striking. An interstellar comet loaded with carbon dioxide, the very gas that once dominated Mars's thick ancient atmosphere, passing by just as the planet's atmospheric pressure sits at less than 1% of Earth's. If you were writing a science fiction story, editors might reject such timing as too convenient to be believable. To understand why the approach of 3I Atlas to Mars captures such attention, we need to step back billions of years to when the red planet was neither red nor dead. The Mars we see today, frozen, desiccated, with an atmosphere so thin that liquid water instantly boils away, is a shadow of what it once was. The evidence is written across the planet's surface in a language of ancient rivers, lake beds, and deltas. Jezero Crater, where NASA's Perseverance rover currently explores, was once a lake fed by river systems. The delta formations preserved there tell us water flowed for extended periods, depositing sediments in patterns identical to those we see in Earth's river deltas today. But it's not just the geological evidence that tells this story. The chemistry of Martian rocks reveals minerals that could only form in the presence of liquid water. Clay minerals, sulfates, and carbonates all speak to a time when Mars had a thick atmosphere capable of supporting a water cycle much like Earth's. That atmosphere was dominated by carbon dioxide, creating a greenhouse effect that kept the planet warm enough for liquid water despite being farther from the Sun than Earth. Current estimates suggest Mars's ancient atmosphere was at least 100 times thicker than today's wisp of gas, possibly approaching Earth-like pressures. So what happened? The answer lies in Mars's core. Unlike Earth, which maintains a strong magnetic field generated by its rotating liquid iron core, Mars's magnetic dynamo shut down early in its history. Without this protective magnetic shield, the solar wind began stripping away the atmosphere, molecule by molecule, a process that has continued for billions of years. The MAVEN spacecraft, orbiting Mars since 2014, has directly measured this ongoing atmospheric loss. Every second, approximately 100 grams of atmosphere escapes to space. It doesn't sound like much, but over billions of years, it's enough to transform a potentially habitable world into the freeze-dried desert we see today. In July 2024, Perseverance made a discovery that added new urgency to our understanding of Mars's past. In a rock sample called Cheyava Falls, collected from the edge of an ancient river valley, the rover found peculiar patterns, leopard spot textures containing iron and phosphate minerals, surrounded by organic molecules. On Earth, similar patterns are often associated with microbial life. NASA was careful not to claim the discovery of life. These patterns could form through purely geological processes, but they represented one of the most intriguing potential biosignatures ever found on Mars. If the red planet once hosted life when it had its thick, CO2-rich atmosphere and flowing water, these might be its fossilized remains. And now, as if responding to this discovery, an interstellar visitor approaches, carrying within its frozen nucleus exactly the kind of chemistry Mars has been losing to space for eons. The significance of 3I Atlas's unusual chemistry becomes clear when we consider what Mars needs most. The red planet's current atmosphere is already 95% carbon dioxide, but there's simply not enough of it. The total atmospheric pressure is less than 1% of Earth's, far too thin to create meaningful greenhouse warming or allow liquid water to exist on the surface. If you could somehow thicken Mars's atmosphere while maintaining its current CO2-dominated composition, you would begin to recreate the conditions that once made the planet potentially habitable. The greenhouse effect would trap solar heat, raising surface temperatures. Higher atmospheric pressure would allow water to exist in liquid form. The planet could, theoretically, begin its journey back toward habitability. Of course, we need to be clear about scales here. A single comet, even one as CO2-rich as 3I Atlas, carries nowhere near enough gas to meaningfully alter a planetary atmosphere. The comet's nucleus is estimated to be between 1 and 5 kilometers in diameter. Even if it were pure frozen CO2, which it isn't, and even if all of that material somehow ended up in Mars's atmosphere, which it won't, the effect would be negligible. Mars has been losing atmosphere for billions of years. The amount of gas that has escaped to space dwarfs anything a single comet could deliver. We're talking about the difference between losing an ocean and gaining a cup of water. But the chemistry is symbolically perfect, and that's what makes this encounter so thought-provoking. It's as if the universe is showing us a demonstration of what Mars needs, even if the scale is impossibly small. The comet carries CO2 for greenhouse warming, water for potential biology, and organic compounds for chemical complexity, essentially a starter kit for planetary habitability, just in the wrong proportions. Some researchers have speculated about whether repeated deliveries of cometary material over geological timescales could meaningfully contribute to planetary atmospheres. We know that Earth's water likely came, at least in part, from cometary impacts early in the solar system's history. Could a similar process work for atmospheric gases? The mathematics aren't encouraging. Even if comets like 3I Atlas struck Mars regularly, say one every 1,000 years, it would take longer than the current age of the universe to accumulate enough gas to significantly thicken the atmosphere. And that's assuming none of the delivered gas escapes to space, which it certainly would, given Mars's weak gravity and lack of magnetic field. Yet the coincidence remains striking. Just as we're discovering possible signs of ancient life on Mars, life that would have required exactly the kind of thick CO2 atmosphere the planet has lost, an interstellar visitor arrives carrying concentrated doses of that very gas. Mark your calendars. October 3rd, 2025. On this date, 3I/Atlas will sweep past Mars at its closest approach, approximately 28 to 30 million kilometers from the red planet. The encounter will occur while both objects are on the far side of the Sun from Earth's perspective, hidden in our star's glare. This solar conjunction isn't unusual or suspicious. It's a predictable consequence of orbital mechanics. As objects move through the solar system on different paths at different speeds, they periodically align in ways that place the Sun between Earth and the object of interest. We experience this regularly with planets. Mars itself goes through solar conjunction approximately every 2 years. But the timing creates a unique observational challenge. Just when 3I Atlas is most interesting, passing close to Mars while approaching peak activity, Earth-based telescopes will be blind to the event. For several weeks in late September through October, the comet will be unobservable from our planet. This is where the European Space Agency's Mars orbiters become crucial. Mars Express carries cameras and spectrometers that could potentially image the comet and analyze its composition. The Trace Gas Orbiter, with its sophisticated atmospheric chemistry instruments, might detect any interaction between the comet's coma and Mars's upper atmosphere, though such interactions would be extremely subtle if they occur at all. The closest approach distance of 30 million kilometers is enormous by human standards, but relatively close in cosmic terms. For comparison, it's about 1/5 the distance between Earth and the Sun. The comet will be close enough that Mars's gravity will measurably affect its trajectory, though the deflection will be tiny. As 3I Atlas approaches perihelion on October 29-30, it will be just inside Mars's orbit, approximately 1.4 astronomical units from the Sun. This is the point of maximum solar heating, when we expect the comet's outgassing to peak. The frozen CO2 that has remained stable for millions of years in interstellar space will sublime directly to gas, creating an expanding cloud around the nucleus. The scale of this outgassing is difficult to imagine. A typical comet can lose millions of tons of material during a close solar passage. For 3I Atlas, with its CO2-dominated composition, the activity could be even more dramatic. CO2 sublimes at lower temperatures than water ice, meaning it begins outgassing farther from the Sun and potentially more violently. Will any of this gas reach Mars? The physics say no. The comet is too far away. The gas expands too quickly into the vacuum of space, and Mars's gravity is too weak to capture any significant amount. But the image is compelling. An interstellar visitor, loaded with the very gases Mars needs, passing tantalizingly close to the planet that lost those same gases eons ago. The story of 3I Atlas intersects with another timeline that adds layers to this cosmic coincidence. Let's step back to fully appreciate the convergence of events. In February 2021, NASA's Perseverance rover touched down in Jezero crater on Mars. Its mission was to search for signs of ancient microbial life and collect samples for eventual return to Earth. For over 3 years, the rover methodically explored the crater, analyzing rocks, taking photographs, and drilling core samples. In July 2024, Perseverance made what might be its most significant discovery. The Cheava Falls rock sample showed features that, on Earth, are often associated with ancient microbial life. Leopard spot patterns containing specific minerals and organic molecules arranged in ways that suggested, though didn't prove, biological processes. NASA announced these findings in September 2024, generating worldwide attention. For the first time, we had potential biosignatures from Mars, not definitive proof of life, but compelling enough to justify the enormous expense and complexity of a sample return mission. Fast forward to July 1, 2025. The Atlas Telescope network detects an unusual object. Within days, it's confirmed as only the third interstellar visitor ever discovered. Within weeks, its unusual CO2-rich chemistry is revealed. By August 2025, orbital calculations show that 3I ATLS will pass close to Mars in October. The same planet where we just discovered potential signs of ancient life will receive a close visit from an interstellar comet carrying the very atmospheric components that planet lost. The timing seems almost orchestrated. If you were to design a sequence of events to maximize human interest in Mars and atmospheric science, you could hardly improve on what actually occurred. First, discover possible ancient life. Then, identify what that life would have needed: a thick CO2 atmosphere. Finally, have an interstellar visitor arrive carrying exactly those components. But we must resist the temptation to see design where there is only coincidence. The universe is vast and old. Given enough time and enough events, remarkable alignments will occur purely by chance. The fact that we happen to be here to witness this particular alignment doesn't make it meaningful in any cosmic sense. Or does it? This is where we enter the realm of speculation, clearly marked as such. Let's be absolutely clear. What follows is speculation. There is no evidence that 3I or Atlas is anything other than a natural comet that happens to have unusual chemistry and interesting timing. But the human mind is designed to see patterns, and the patterns here are admittedly intriguing. Consider the odds. Interstellar objects pass through our solar system regularly. Current estimates suggest thousands per year, but most are too small or too distant to detect. We've only spotted 3 in human history. For one of those 3 to have chemistry so specifically relevant to Mars, and to pass by Mars at just this moment in human exploration, seems statistically improbable. But improbable doesn't mean impossible, or even necessarily meaningful. Win the lottery, and the odds of your specific numbers coming up were millions to 1. But someone had to win, and pray the fact it was you. Similarly, if interstellar objects pass through regularly, some of them will have interesting chemistry and timing purely by chance. Still, let's explore some speculative possibilities, always remembering these are thought experiments, not scientific theories. What if the universe has natural mechanisms that tend to deliver atmospheric components to planets that have lost them? We know that Jupiter's gravity protects Earth by deflecting many potentially dangerous comets and asteroids. Could there be larger-scale gravitational or chemical processes that naturally route certain types of objects towards certain types of planets? What if 3I/Atlas isn't alone? What if it's part of a stream of similar objects, all ejected from the same stellar system, all carrying similar chemistry? We might be seeing just one member of a vast river of interstellar material flowing through our galactic neighborhood. What if the timing isn't coincidental, but observational? Perhaps CO2-rich interstellar comets are common, but we only noticed this one because we're actively studying Mars and atmospheric chemistry. Our increased interest and capability led to the discovery, rather than the discovery happening at a meaningful time. These are interesting thoughts, but they remain speculation without evidence. The scientific method requires us to default to the simplest explanation that fits the facts. 3I/Atlas is a natural comet with unusual but not impossible chemistry, passing through our solar system on a random trajectory that happens to bring it relatively close to Mars. To put 3I/Atlas in context, we need to examine what its predecessors taught us about interstellar objects. Oumuamua, discovered in October 2017, was our first confirmed interstellar visitor. It immediately challenged our expectations. Instead of being a typical comet, it showed no coma or tail despite passing close to the Sun. Its shape was highly unusual, extremely elongated, perhaps 6 to 10 times longer than it was wide. Most mysteriously, it showed acceleration that couldn't be explained by gravity alone. Various hypotheses were proposed for Oumuamua's strange acceleration. Outgassing of hydrogen, too faint to detect. A light sail effect, from solar radiation pressure on an unusually thin, flat object. Some even speculated about artificial origin, though no evidence supported this beyond the unusual acceleration. Oumuamua taught us that interstellar objects could be detected with existing technology, opening an entirely new field of astronomy. It also showed us that these objects might be far more diverse than expected. Our models, based on objects from our own solar system, might not apply to visitors from other stars. 2I Borisov, discovered in August 2019, was in many ways the opposite of Oumuamua. It looked exactly like comets from our own solar system. It had a clear coma, a typical tail, and familiar chemistry dominated by water ice. If we hadn't known its trajectory was hyperbolic, we might have assumed it was a local comet. Borisov taught us that at least some interstellar objects are remarkably similar to solar system comets. This suggests that the basic processes of comet formation might be universal, operating similarly across different stellar systems. It was comforting in a way. The universe beyond our solar system wasn't completely alien.
Now 3I Atlas adds a third data point. Unlike the mysterious Oumuamua or the familiar Borisov, Atlas is recognizably a comet, but with chemistry significantly different from what we typically see. It's teaching us that while comet formation might be universal, the specific chemistry can vary dramatically depending on the conditions in different stellar systems. 3 objects aren't enough to draw firm conclusions about the population of interstellar visitors, but patterns are beginning to emerge. These objects seem to fall into different categories: rocky asteroids, typical comets, and now chemically unusual comets. The diversity suggests that interstellar space contains a rich variety of objects, each carrying information about its parent system. As we learn more about 3I Atlas, certain aspects of its approach to Mars become even more intriguing, not because they suggest anything artificial or designed, but because they highlight natural processes that could have profound implications for planetary evolution. Mars's atmosphere isn't static. It varies with the seasons, thickening and thinning as CO2 freezes out at the polar caps in winter and sublimates in summer. Dust storms can temporarily warm the planet by trapping heat. Solar activity can strip away atmospheric gases or, conversely, protect the atmosphere by deflecting cosmic rays. The arrival of 3I Atlas coincides with Mars's northern hemisphere autumn, approaching winter solstice. This is when the northern polar cap grows as CO2 freezes out of the atmosphere. The planet's atmosphere is near its annual minimum, making the contrast with the CO2-rich comet even more stark. If we think about this on geological timescales, the passage of comets like 3I ATLS might have played a role in Mars's atmospheric evolution. Not individual comets, which, as we've established, carry too little material to matter, but the cumulative effect of many comets over billions of years. We know that early in the solar system's history, during what's called the Late Heavy Bombardment, about 4 billion years ago, the inner planets were pelted with comets and asteroids. This bombardment might have delivered water to Earth and other volatiles to all the terrestrial planets. Could Mars have received atmospheric gases this way? The evidence suggests yes, but with a crucial difference. Earth's stronger gravity and magnetic field allowed it to retain delivered volatiles. Mars, smaller and magnetically unprotected, would have lost much of what it gained. It's like trying to fill a bucket with holes in it. You can add water, but it leaks out faster than you can pour it in. 3I Atlas, in a sense, represents what Mars has been experiencing for billions of years. Temporary visitors delivering atmospheric components that the planet cannot retain. It's a cosmic tragedy played out in slow motion, a planet trying and failing to maintain the conditions necessary for life.
Let's examine more closely what Perseverance actually found in July 2024, because understanding these potential biosignatures helps explain why the arrival of 3I/Atlas feels so significant. The rock, named Cheava Falls, was found at the edge of an ancient river valley in Jezero crater. It's about 1 meter by 0.6 meters, and from a distance it looks unremarkable. But when Perseverance examined it closely with its Sherlock and Pixel instruments, remarkable features emerged.
The rock contains dozens of small, light-colored spots surrounded by dark rings, creating the leopard spot pattern that caught scientists' attention. Each spot is millimeters across, containing iron and phosphate minerals. Between these spots, the instruments detected organic molecules, carbon-based compounds that are the building blocks of life as we know it. On Earth, similar patterns can form when microbial life creates chemical reactions that precipitate minerals. Bacteria often create similar spots as they process nutrients and energy from their environment. The combination of specific minerals, organic molecules, and distinctive patterns makes Cheava Falls one of the most intriguing rocks ever found on Mars.
But NASA scientists are careful to note that non-biological processes could create similar features. Chemical reactions between water and rock, without any life involved, can sometimes produce spotted patterns. Organic molecules can form through purely chemical processes. They've been found in meteorites and comets, where life is unlikely to exist. This is why sample return is so crucial. Only by bringing pieces of Cheava Falls back to Earth, where they can be studied with instruments far too large and complex to send to Mars, can we determine whether these features are truly biological.
The Mars Sample Return Mission, a joint effort between NASA and the European Space Agency, aims to collect the samples Perseverance has been gathering and bring them to Earth by the early 2030s. It will be one of the most complex space missions ever attempted, requiring multiple spacecraft, a launch from Mars's surface, and precise orbital rendezvous.
If those samples confirm that Cheava Falls contains genuine biosignatures, it would be one of the most profound discoveries in human history. Life, even simple microbial life, would have existed on Mars when the planet had a thick atmosphere and flowing water.
And this is where 3I Atlas enters the narrative. If Mars once had life, that life required specific conditions: liquid water, appropriate temperatures, and a thick atmosphere to maintain both. The CO2 that 3I Atlas carries in such abundance is exactly what that ancient Martian life would have needed. To understand the connection between 3I Atlas's chemistry and potential Martian life, we need to explore what makes a planet habitable. Life as we know it requires liquid water, not ice, not vapor, but liquid water where chemical reactions can occur. Maintaining liquid water on a planetary surface requires a delicate balance of temperature and pressure. Too cold and water freezes. Too hot and it boils away. Too little atmospheric pressure and liquid water cannot exist at all. It sublimes directly from ice to vapor. Mars today fails all these requirements. Average temperatures are about -80 degrees Fahrenheit, -60 degrees Celsius, cold enough to freeze CO2 out of the atmosphere. Atmospheric pressure is less than 1% of Earth's, so low that liquid water cannot exist on the surface. Any water that somehow melted would immediately boil away in the thin atmosphere. But ancient Mars was different. The evidence is everywhere: dried river channels, lake beds, minerals that only form in water. For liquid water to have existed, Mars must have had a thicker atmosphere, creating greenhouse warming and sufficient pressure. Carbon dioxide is the key to both. As a greenhouse gas, carbon dioxide traps heat from the sun, warming the planet. More carbon dioxide means more warming. And as the main component of Mars's atmosphere then and now, it provides the pressure necessary for liquid water to remain stable. The organic molecules detected in Cheava Falls add another dimension. Life requires not just water, but carbon-based chemistry. Organic molecules are the building blocks, amino acids that form proteins, nucleotides that form DNA and RNA, lipids that form cell membranes. 3I Atlas contains all of these prerequisites in its frozen nucleus. Water ice, though less abundant than in typical comets. CO2 in extraordinary abundance. Organic compounds, including the cyanide species that create its greenish glow. It's carrying the raw ingredients for both habitability and life. Of course, delivering ingredients doesn't create life. You can have all the components for a cake, but without the right conditions and processes, you just have a pile of flour, eggs, and sugar. Similarly, Mars receiving cometary deliveries of water, CO2, and organics doesn't automatically make it habitable or inhabited. But the symbolic parallels are striking.
At the very moment we're discovering potential evidence of ancient Martian life, an interstellar visitor passes by carrying concentrated doses of exactly what that life would have needed. It's as if the universe is showing us the recipe even as we uncover evidence of the cake. As September 2025 transitions to October, 3I Atlas begins to disappear from Earth's view. The comet's position relative to Earth and the Sun means it's becoming increasingly difficult to observe, lost in the Sun's glare as it approaches solar conjunction. This isn't unusual or suspicious, it's simple geometry. As Earth and Mars orbit the Sun at different speeds and distances, there are regular periods when Mars is on the opposite side of the Sun from Earth. During these conjunctions, communication with Mars rovers and orbiters becomes impossible for about 2 weeks. The same geometry that blocks our radio signals also blocks our telescopic view of anything near Mars. For 3I Atlas, this means the most interesting part of its journey through the inner solar system will be largely unobserved from Earth. We'll lose sight of it in late September, and it won't become visible again until late November. During those crucial weeks, the comet will pass Mars, reach perihelion, and undergo maximum heating and outgassing. This observational gap frustrates astronomers, but also adds to the mystery. What will happen when 3I/Atlas is at its most active, passing closest to Mars while hidden from our view? Will the European Space Agency's Mars orbiters successfully observe the encounter? Will the comet fragment under thermal stress, as many comets do near perihelion? Will its chemistry change as different layers of the nucleus are exposed? The Mars orbiters face their own challenges in observing 3I Atlas. These spacecraft were designed to study Mars, not to track fast-moving comets. Their instruments are optimized for looking down at the planet's surface or analyzing its thin atmosphere, not for observing objects millions of kilometers away. Mars Express has cameras that could potentially image the comet, but tracking a fast-moving object while orbiting Mars requires complex spacecraft maneuvers. The Trace Gas Orbiter's instruments could detect any chemical interaction between the comet and Mars's atmosphere, but such interactions, if they occur at all, would be extremely subtle. There's also the question of priority. These missions have their own scientific objectives studying Mars. Diverting time and resources to observe 3I Atlas means less time for their primary missions. The scientific value has to be weighed against the opportunity cost. Despite these challenges, both ESA and NASA have expressed strong interest in attempting observations. The chance to study an interstellar comet from Mars' orbit is unprecedented. Even limited data could provide valuable insights into the comet's composition and behavior. On October 29th or 30th, 2025, 3I Atlas will reach perihelion, its closest approach to the Sun at approximately 1.4 astronomical units. This is the moment of maximum drama in any comet's journey through the inner solar system, when solar heating reaches its peak and the frozen nucleus experiences the greatest thermal stress. For a typical water-ice-dominated comet, perihelion can be a violent event. The rapid heating causes explosive outgassing, sometimes fragmenting the nucleus entirely. We've observed many comets break apart at perihelion, torn apart by the combination of thermal stress and tidal forces. The fate of 3I Atlas at this crucial moment remains uncertain.
But 3I Atlas isn't typical. Its CO2-rich composition means it's been outgassing since much farther from the Sun than a water ice comet would. CO2 sublimes at lower temperatures, so the comet has been active and losing mass more gradually. This might actually protect it from the kind of catastrophic fragmentation that destroys other comets. The perihelion distance of 1.4 AU places 3I Atlas just inside Mars's orbit, but still relatively far from the Sun compared to many comets. Some comets pass within Mercury's orbit, or even graze the Sun's atmosphere. At 1.4 AU, 3I Atlas will experience significant heating, but not the extreme conditions that destroy sun-grazing comets. What we expect to see when observations resume in November is a comet transformed. The intense solar heating will have stripped away the outer layers of the nucleus, possibly exposing pristine material that's been frozen since the comet formed around another star millions or billions of years ago. The chemistry might be different, the outgassing rate changed, the coma structure altered. This transformation is scientifically valuable. By comparing pre- and post-perihelion observations, astronomers can learn about the comet's internal structure. Is it homogeneous throughout, or layered like an onion? Is the CO2 concentration consistent through the nucleus, or was it just a surface phenomenon? These questions can only be answered by observing how the comet changes during its solar passage. The timing of perihelion, coming just weeks after the Mars encounter, adds another dimension to consider. The comet will be at maximum activity while still relatively close to Mars's orbital path. Any debris shed during perihelion outbursts will continue along similar trajectories, potentially creating a sparse meteor stream that Mars might encounter in future orbits. This raises an intriguing, if highly speculative, possibility. Could Mars experience meteor showers from interstellar debris? The odds are astronomically small, but if 3I Atlas sheds significant material near Mars's orbit, the red planet might occasionally encounter these particles in coming years or decades. Interstellar meteors burning up in Mars's thin atmosphere. It's a poetic image, even if unlikely. To fully appreciate what 3I Atlas represents, we need to zoom out and consider the broader processes of planetary atmospheric evolution. Every rocky planet in our solar system has experienced atmospheric change, but none more dramatically than Mars. Venus, Earth, and Mars started with roughly similar conditions. All three had volcanic activity releasing gases from their interiors.
All three likely had water delivered by comets and asteroids during the late heavy bombardment. All three had the potential to develop thick atmospheres and possibly support life. But their evolutionary paths diverged dramatically. Venus experienced a runaway greenhouse effect, its proximity to the Sun causing water to evaporate, hydrogen to escape to space, and CO2 to accumulate until surface temperatures reached 900 degrees Fahrenheit. Earth found the sweet spot, its distance from the Sun allowing liquid water oceans that absorbed CO2, its magnetic field protecting the atmosphere from solar wind stripping. Mars fell victim to its small size. With only 11% of Earth's mass, it cooled quickly, its core solidified, shutting down the magnetic dynamo. Without magnetic protection, solar wind began stripping the atmosphere. Lower gravity meant gas molecules could more easily reach escape velocity. The planet entered a death spiral of atmospheric loss, cooling, and desiccation.
The role of cometary delivery in this process remains debated. We know comets can deliver volatiles, water, CO2, and other gases. But how much did they contribute to planetary atmospheres versus volcanic outgassing? For Earth, current models suggest comets contributed perhaps 10% of our water, with the rest coming from volcanism and water-bearing minerals in the planet's building blocks. For Mars, the calculation is different. Its weaker gravity means cometary impacts would have been more destructive, potentially blasting away as much atmosphere as they delivered. It's like trying to fill a glass by throwing ice cubes at it. You add water, but you also break the glass.
3I Atlas, in this context, represents a process that's been ongoing for billions of years. Comets arrive, deliver volatiles, and depart. For planets like Earth, with strong gravity and magnetic protection, these deliveries accumulate over time. For Mars, they're temporary contributions to an atmosphere that's steadily leaking away. The interstellar nature of 3I Atlas adds a new dimension. If interstellar comets regularly pass through our solar system, they've been contributing exotic chemistry from other star systems throughout planetary history. The building blocks of planets and potentially life might be more cosmopolitan than we realized, drawn from across the galaxy rather than just our local stellar neighborhood.
As we observe more interstellar objects, scientists are beginning to look for patterns that might reveal larger truths about our galaxy. 3 objects aren't enough for statistical analysis, but they're enough to start asking questions. Are CO2-rich comets like 3I Atlas common in interstellar space? Or is this visitor unusual? The answer matters for understanding stellar system formation. If CO2-rich comets are common, it suggests many stellar systems have different temperature structures or chemical abundances than our own. If they're rare, 3I Atlas might come from an unusual stellar environment. The trajectories of interstellar objects also contain information. By tracing back their paths, astronomers try to identify possible source stars. For 3I Atlas, the calculations point toward the general direction of the constellation Sagittarius, but the specific star system remains unknown. The comet has been traveling for so long that stellar positions have changed significantly. The speed distribution of interstellar objects tells us about the dynamics of our galaxy. Objects ejected from planetary systems during formation should have certain velocity patterns. Objects stripped from stars by galactic tides should have different patterns. By building a catalogue of interstellar visitor velocities, we can learn about the processes that populate interstellar space with wandering objects.
The chemical diversity is perhaps most intriguing. Oumuamua appeared rocky or metallic. Borisov was a typical water-ice comet. 3I Atlas is CO2 dominated. This diversity suggests that interstellar space contains a rich variety of objects, each preserving information about its unique formation environment. Some researchers have proposed that interstellar objects might actually outnumber stellar system-bound objects in the galaxy. If every star system ejects numerous comets and asteroids during planet formation, and these objects then wander for billions of years, the galaxy could be full of such wanderers. We're just beginning to detect the tip of an enormous iceberg. The passage of 3I Atlas has implications for future Mars exploration, even if the comet itself has minimal direct effect on the planet. The encounter highlights questions about Mars's atmospheric history and potential future that are central to human exploration plans. Current plans for human missions to Mars must deal with the planet's thin atmosphere and lack of accessible water. The atmosphere is too thin to provide useful pressure for habitats or to slow spacecraft during landing, but thick enough to create dangerous dust storms. Water exists mainly as ice at the poles, or possibly as underground liquid reservoirs. Understanding how Mars lost its atmosphere and whether that process could be reversed or at least slowed is crucial for long-term human presence. Could we somehow thicken Mars's atmosphere using its own CO2 reserves frozen at the poles? Could cometary impacts be artificially induced to deliver volatiles? These questions move from science fiction toward scientific possibility as our capabilities advance. 3I Atlas demonstrates that the raw materials Mars needs exist in space, even if delivering them effectively remains beyond our current technology. The comet's CO2-rich chemistry is exactly what terraforming enthusiasts dream of delivering to Mars, just in impossibly small quantities. The Mars Sample Return mission takes on additional significance in this context. If the samples confirm ancient life on Mars, it proves the planet was once habitable. Understanding exactly what conditions that life required and how long they persisted could inform future attempts to restore Mars habitability, even if only in limited, controlled environments. The timing of 3I Atlas's passage also affects mission planning. The Mars orbiters attempting to observe the comet will gain experience tracking fast-moving objects from Mars orbit.
This experience could prove valuable for future missions that might need to monitor asteroids or comets near Mars, either for scientific study or planetary defense.
When 3I Atlas emerges from behind the Sun in late November 2025, astronomers will eagerly resume observations. The comet will have passed its most dramatic phase, but the post-perihelion period offers unique scientific opportunities. First, we'll be able to assess how the comet survived perihelion. Did it fragment? Did its chemistry change? Is it still actively outgassing, or has the surface been depleted of volatiles? These observations will tell us about the comet's structure and composition in ways that pre-perihelion observations couldn't.
The comet will be receding from both the Sun and Earth, gradually fading as it returns to interstellar space. But modern telescopes can track objects far fainter than ever before. We should be able to follow 3I Atlas for months, possibly years, as it departs our solar system. This extended observation period is scientifically valuable. As the comet cools, different volatiles will stop sublimating at different temperatures. By watching which gases disappear from the spectrum first, astronomers can better understand the comet's chemistry and structure. It's like watching a complex chemical reaction in reverse, each component shutting down at its characteristic temperature.
The trajectory of 3I Atlas as it leaves will also be carefully measured. Any deviation from the expected path could indicate additional outgassing, fragmentation, or even the influence of non-gravitational forces like those that affected Oumuamua. Every data point helps refine our models of how interstellar objects behave. There's also the possibility of discovering companion objects. Some comets travel in groups, fragments of a larger body that broke apart long ago. If 3I Atlas has companions, they might become visible as they too approach the Sun. Discovering a family of interstellar objects would be unprecedented and scientifically revolutionary. The arrival of 3I Atlas has captured public imagination in ways that pure science rarely does. The combination of an interstellar visitor, unusual chemistry, and the Mars connection creates a narrative that resonates beyond the astronomical community. Science museums and planetariums worldwide have created exhibits about interstellar objects, using 3I Atlas as the centerpiece. The comet has become a teaching tool, helping explain everything from orbital mechanics to spectroscopy to the search for life on Mars. Amateur astronomers, though unable to see the faint comet directly, have contributed to the observation campaign. By precisely timing the positions of stars that 3I Atlas passes near, amateurs help refine the comet's trajectory. This citizen science contribution continues a long tradition of amateur involvement in comet studies. The media coverage has been intense, but sometimes sensationalized. Headlines about alien comets and Mars bombardment misrepresent the science, but reflect genuine public fascination. The challenge for scientists is communicating the real wonder of 3I Atlas without feeding misconceptions or conspiracy theories.
Online discussions reveal the psychological impact of interstellar visitors. For many, these objects make the universe feel less lonely. If material routinely travels between star systems, then the stars aren't isolated islands, but part of an interconnected galaxy. We're not alone in a cosmic sense, even if we haven't found life. Others see darker implications. If objects from other star systems routinely pass through ours, could they carry dangers? Not life necessarily, but unknown chemistry or materials that could affect planets in unexpected ways. These fears, while scientifically unfounded for objects like 3I Atlas, reflect deep anxieties about our cosmic vulnerability. As 3I Atlas continues its journey, what lessons can we draw from this remarkable visitor? First, the universe is more dynamic and interconnected than we imagined. Material routinely travels between star systems, carrying chemistry and possibly even the building blocks of life across galactic distances. We are part of a cosmic ecosystem that extends far beyond our solar system. Second, our ability to detect and study these visitors is rapidly improving. From 0 known interstellar objects before 2017 to 3 by 2025, with more surely to come. Each detection teaches us not just about that specific object, but about the population of interstellar wanderers and the processes that create them. Third, coincidences happen, and they can be meaningful without being designed. The passage of a CO2-rich comet near Mars, just as we discover potential Martian biosignatures, is remarkable timing. But remarkable things happen in a universe with billions of stars, planets, and wandering objects. The meaning comes from our observation and interpretation, not from cosmic design. Fourth, interdisciplinary science produces the richest insights. Understanding 3I Atlas requires astronomy, chemistry, geology, and even biology. The comet's significance emerges from connections between different fields, reminding us that nature doesn't respect academic boundaries. Fifth, public engagement with science matters. The excitement about 3I Atlas translates into support for space missions, funding for telescopes, and inspiration for the next generation of scientists. Even when the public narrative strays from strict scientific accuracy, the underlying enthusiasm drives progress. 3I Atlas won't be our last interstellar visitor. Based on the detection rate so far, astronomers expect to find several interstellar objects per year once the Vera Rubin Observatory comes online. This next-generation telescope will scan the entire visible sky every few nights, detecting objects far fainter than current surveys can see. What might we find? Statistical models suggest most interstellar objects are small, perhaps meter-sized or less. We only detect the largest ones with current technology. Future surveys might reveal that Earth regularly encounters interstellar dust and small meteoroids,
material from other star systems burning up in our atmosphere unnoticed.
We might find interstellar objects with even more exotic chemistry than 3I Atlas. Comets dominated by methane, ammonia, or compounds we've never seen in our solar system. Each would tell us about different stellar environments and formation conditions. There's the tantalizing possibility of finding an interstellar object on an Earth-approaching trajectory. While the odds of an actual collision are infinitesimally small, a close approach would offer unprecedented opportunities for study. We could potentially send a spacecraft to intercept it, collecting samples of material from another star system.
Some researchers dream of finding a captured interstellar object, one that entered our solar system at just the right angle and speed to be gravitationally captured into a long-term orbit. Such an object would become a permanent interstellar ambassador, available for detailed study whenever we develop the capability to reach it. The search for patterns will intensify as we build a larger catalogue. Do interstellar objects arrive from preferred directions? Are certain chemistries more common? Can we identify source regions in our galaxy that produce more wanderers? Each question opens new avenues for understanding our cosmic neighborhood. The story of 3I Atlas interweaves with another major astronomical endeavor, the Mars Sample Return Mission. Currently targeted for the early 2030s, this mission will bring pieces of Mars to Earth, including the potentially biosignature-bearing Chayava Falls rock. If those samples confirm ancient life on Mars, it will contextualize encounters like the 3I Atlas passage in a new light. We'll know that Mars once supported life when it had a thick CO2 atmosphere and flowing water. Every comet passing Mars, whether from our solar system or beyond, becomes part of the story of a planet that lost its habitability.
There's even the remote possibility that Mars samples could contain interstellar material. If comets like 3I Atlas have been passing through our solar system throughout history, some might have impacted Mars. Exotic isotope ratios or unusual minerals could fingerprint material from other star systems, preserved in Martian rocks for billions of years.
The technology developed for Mars sample return could eventually be applied to interstellar objects. If we can retrieve samples from Mars, perhaps we could one day retrieve samples from an interstellar comet or asteroid. The engineering challenges are immense, but not necessarily insurmountable. The passage of 3I Atlas raises philosophical questions that extend beyond astronomy. What does it mean for our understanding of Earth's and possibly life's cosmic context? If interstellar objects regularly deliver material between star systems, then planets aren't closed systems but open ones, constantly exchanging material with the wider galaxy. Earth has likely received tons of interstellar material over its history. We might literally be made of star stuff from multiple star systems, not just the Sun's original nebula. This cosmic material exchange has implications for astrobiology. The panspermia hypothesis, The idea that life spreads between planets or even star systems via meteoroids becomes more plausible if interstellar objects are common. While 3I Atlas shows no signs of carrying life, it demonstrates that the vectors for panspermia exist. The timing coincidence, discovering potential biosignatures on Mars just as a CO2-rich interstellar comet passes by, highlights how human observation creates meaning. The universe doesn't care about our discoveries or their timing. But we do, and that human perspective, that search for patterns and meaning, is itself a remarkable cosmic phenomenon. There's also humility in recognizing that Earth and our solar system aren't unique or isolated. We're one planetary system among billions in our galaxy, sharing material, chemistry, and possibly even life with our cosmic neighbors. 3I Atlas is a reminder of our cosmic citizenship. The observation of 3I Atlas showcases both the capabilities and limitations of current astronomical technology. Detecting a kilometer-sized object at astronomical unit distances requires incredibly sensitive instruments and sophisticated data processing. The Atlas system that discovered the comet uses relatively modest 0.5-meter telescopes, but couples them with advanced CCDs and automated detection software. Every night, these telescopes capture thousands of images, comparing them to identify objects that move against the background stars. Machine learning algorithms help distinguish real objects from artifacts, cosmic rays, and noise. Once detected, larger telescopes take over. The James Webb Space Telescope, with its 6.5-meter mirror and infrared instruments, can analyze the comet's chemistry in unprecedented detail. Ground-based giants like the Very Large Telescope and Keck Observatory provide complementary observations in visible light. But even our best instruments struggle with objects like 3I Atlas. The comet is faint, fast-moving, and chemically complex. Every observation pushes against technical limits. Exposure times must be precisely calculated to capture enough light without the comet's motion blurring the image. Spectroscopic analysis requires hours of observation to achieve sufficient signal-to-noise ratios. The solar conjunction problem highlights another limitation. When objects pass near the Sun from Earth's perspective, they become unobservable for weeks or months. No amount of technological advancement can overcome basic geometry. This is why space-based observations from multiple vantage points, like the Mars Orbiter's potential observations of 3I Atlas, are so valuable. The story of 3I Atlas ultimately connects to humanity's greatest quest, understanding whether life exists beyond Earth. Every piece of this cosmic puzzle, the comet's chemistry, Mars's biosignatures, planetary atmospheres, relates to this fundamental question. We now know that the building blocks of life are common throughout the universe. Organic molecules form in interstellar space, in comets, on asteroids. Water is abundant. Planets exist around most stars. The ingredients for life appear universal. But ingredients don't guarantee the recipe works. The conditions for life to emerge and persist might be far more restrictive than the availability of raw materials. Mars had the ingredients: water, organic molecules, energy sources. But did life actually arise? And if it did, why did it apparently disappear? 3I Atlas adds another variable to consider: interstellar delivery of materials. If life's building blocks routinely travel between star systems, then life might be more cosmopolitan than we imagined, not necessarily spreading as living organisms, but as the chemical precursors that make life possible. The search continues on multiple fronts. Mars sample return will look for definitive biosignatures. The James Webb Space Telescope examines exoplanet atmospheres for signs of life. Radio telescopes listen for artificial signals. And now, we also study interstellar visitors for clues about chemistry and potentially biology in other star systems. As we reach the end of our journey with 3I Atlas, it's worth reflecting on how we choose to interpret cosmic events. The coincidences surrounding this interstellar visitor, its unusual chemistry, its passage near Mars, the timing with biosignature discoveries, create a pattern that begs for explanation. We could invoke conspiracy theories, alien intervention, or cosmic design. These explanations offer the comfort of purpose and meaning, suggesting that events happen for reasons we can understand. Or we can embrace the scientific perspective, that coincidences happen in a vast universe, that patterns emerge from random events, that meaning comes from our observation and interpretation rather than cosmic intention. This view might seem less comforting, but it contains its own profound wonder. The real 3I Atlas, a chunk of frozen chemistry from another star, following the inexorable laws of physics through our solar system, is remarkable enough without embellishment. It connects us to other star systems, demonstrates the galaxy's chemical diversity, and provides a natural experiment in planetary atmospheric chemistry. As October 2025 approaches and 3I Atlas makes its closest approach to Mars, we are witnessing something that has probably happened countless times in the solar system's history, but never before with human observers capable of understanding its significance. We are the universe becoming aware of itself, capable of recognizing an interstellar visitor and pondering its meaning. The comet will pass Mars, round the Sun, and begin its long journey back to interstellar space. It won't deliver enough gas to thicken Mars's atmosphere or resurrect the planet's lost habitability. It won't carry secret messages or alien technology. It will simply follow its trajectory, sublime its ices, and gradually fade from view. But in its passage, 3I Atlas will have taught us about the cosmos and our place within it. We'll have learned about interstellar chemistry, refined our understanding of cometary physics, and added another data point to our growing catalogue of cosmic wanderers. Most importantly, We'll have participated in a cosmic moment, observers and interpreters of an event that spans star systems and millions of years. This is the real magic, not in conspiracies or hidden meanings, but in the simple fact that we're here, aware and capable of understanding. As you drift off to sleep tonight, perhaps spare a thought for 3I Atlas, sailing through the darkness between Mars and the Sun. It's a reminder that the universe is vast, dynamic, and full of wonders that require no embellishment to inspire awe.
The stars aren't watching us, but we're watching them. And occasionally they send us visitors like 3I Atlas to remind us that we're part of something far larger than our single world. In that connection, in that cosmic citizenship, lies a meaning more profound than any conspiracy could provide. Sweet dreams, fellow travelers. The universe continues its dance, and we're privileged to witness a few steps of its infinite choreography.